Hey, good afternoon, everyone. Thanks for joining us this afternoon on this National Hurricane Conference virtual webinar from us from the National Hurricane Center. I'm Hurricane Specialist Robbie Berg. I'll be one of the moderators here for this session. We'll also have Dan Brown, who's Hurricane Specialist and Warning Coordination Meteorologist, joining us here shortly to help moderate. So this afternoon we have Storm Surge Team Lead Jamie Rhome from the Hurricane Center, who's going to be talking about some of the recent changes to the Storm Surge program at the Hurricane Center, and also some of the things that are new this year and looking ahead to the future. And I suspect we'll also maybe touch a little bit on what happened this past weekend with Tropical Storm Cristobal. Before I turn it over to Jamie, just note that you're free and able to ask questions whenever you'd like during the webinar. You can see on your little GUI there on your screen, you can type in your questions, and what we will try and do is collect some of the best ones and send them over to Jamie's way when he is done talking. So we have an hour and a half for this whole session. We should have plenty of time for Jamie to give his talk and then to answer your questions. So with that, I will now turn it over to Jamie on his talk.
Okay, good afternoon, everyone. This was scheduled maybe a couple of weeks ago, and we decided to, in light of Cristobal, to at least offer the opportunity to talk about that storm as well. So maybe at the end, during the question and answer, we can certainly field any questions you have regarding that particular storm. But for now, we're going to sort of plow through the slides here. And, you know, I'll go ahead and admit up front, some of these slides are a bit technical in nature, owing to we've just gotten a lot of requests or interest of late. Folks kind of want to see behind the scenes or beyond the public-facing products and services and see sort of the science and technology that's changing it and or driving it, and also gotten a lot of requests about where we're going from here. So this will also focus a bit on the future. So quick thing here, and we're going to spend some time on this one because this is actually one of the more powerful slides in the deck. You know, similar to what the hurricane specialists do with the wind speed timing and time of arrival and that sort of stuff, where we have a probabilistic underpinning in all of our forecast products, meaning every single thing we do here is based off a probabilistic framework, and that is also consistent with what their Weather Service forecast offices do. They use this same probabilistic framework, and we kind of want to touch on what this really is, because most people, when they think models, they're used to, you know, these spaghetti diagrams, or, you know, track models, or American model versus European, or that sort of stuff. And I want to sort of help explain what Psurge is. And Psurge really is just a wrapper around slosh. So slosh is the storm surge model that drives all of this, and Psurge is just a probabilistic framework that basically builds the tracks. So you can envision in this panel here, if the official forecast is the, you know, one down the middle, how wide to spread these tracks. I mean, how close they are together as far as how much to fan them out at each of the forecast times is basically what Psurge is doing. And little circles here represent what we call the radius of maximum winds, which is just size. And so what sizes to use, and we're going to talk a bit more about that. It was actually the most critical part of the Cristobal forecast. That's also a part of the probabilistic wrapper. So just again, this is slosh, and actually the probabilities or the error distributions that go into generating the tracks here are based off the 5-year error. Since the hurricane specialists update that every year, we also update it, and that's what's controlling what we call the cross track, which sort of governs the landfall location, or left and right, or west and east in this chart, as well as the along track, which is the forward speed. The forward speed turns out to be really important in places where you have a large tide range, because if you miss the tide or miss the timing by just a few hours, you can miss the total water level forecast by quite a bit. But it also turns out to be very important for certain areas where forward speed is very, the ultimate storm surge. The Cristobal is a great example how just a subtle reduction in the forward speed as it got to landfall is really what drove some of those higher storm surge values that you saw. Obviously, intensity is really, really important. And the parameter here that people just totally forget about, everybody's enamored with intensity, but I'm telling you, size and structure is probably one of the most important aspects of predicting storm surge. And then why do we use a probabilistic frame? Why don't we use other types of models or other types of approaches? Because it's within our directive or our governance language. There's a requirement that all operational forecasts are based off of probabilistic frameworks, and the actual requirement is statistically reliable probabilistic guidance out to 48 hours as of right now, but Congress has asked us to extend that to 72 hours by 2022, and we'll talk quickly about that. And then we use these things called exceedances, and they have to be available to us in AWEPS. So if it's not in AWEPS, AWEPS is a system we use to make our forecasts and disseminate our warnings. If it's not in AWEPS, we can't use it. So a lot of people send us web links. Here's a model. Can you look at it? And that just just running a model just doesn't cut it. It's got to be available to us in the system that we use for making forecasts. And then it has to run on and this is the hard one. If there are any hydrodynamic modelers out there, they'll recognize this. It has to be, the whole thing has to run in 1 hour, our last wall clock time on our operational supercomputer called WCOS. The replacement of WCOS 2 is going in circa 2022, which will get us this new 72-hour thing. Now, this mysterious new plot in the bottom right-hand corner that I've sort of ignored to date is really one of the more interesting plots I've seen for a while. If you haven't seen this was a recent blog post about a month or so ago. And so what you're looking at is on the y-axis, the track error. So this is what how accurate is a model? How off is it? And then on the x-axis is consistency. So this is what you're used to hearing, jumping around. The model jumps all over the place, moves around, left, right, that sort of thing. And then we've plotted on here the three most, historically at least, the three most accurate global forecast models. So the European, the American GFS, and the UK Met. So you want to be in the bottom left-hand corner because that's both more accurate and more consistent. And what jumps off the page here is the official National Hurricane Center forecast absolutely crushes the best available models here. So it's not only more accurate, it's more consistent. And I think we can all appreciate how consistency is as important as accuracy when you're talking about evacuation decision-making or the type of national response that we would normally have in a big hurricane event. So if you haven't seen this plot, you really owe it to yourself to look at this, because often the number one question we get in briefings is, have you seen the European model? Have you seen the GFS model? And the answer is always, well, of course we have, and we factor that into our forecast. And then also what you see often dominating in the media coverage is the so-called American model versus the European model. When you know what, the Hurricane Center forecast just beats them all. So there's something to be learned from this plot, I think, as it pertains to the way hurricanes are covered in media these days. Here's another plot, and I swear this is the last one that we're going to spend so much time on, but it's new, so that's why I want to sort of talk about it. This is what's called a relative operating characteristic diagram. And so it's a way of validating a modeling system or forecast system in a way that's it's pretty demanding. So on this axis, the x-axis is the false alarm rate. So this is cry wolf. So here is 0 cry wolf, here is maximum cry wolf. And then on the y-axis is this probability of detection. How well did you do at actually detecting the event? So up here is a perfect detection, down here is a 0 detection. So where you want to be in life is up in this upper left-hand corner. It's both a very high probability of detection and a low cry wolf number here. And then you don't want to be along this line right here because this is no skill. So this is terrible. And where you're hoping to get in life is this upper left-hand corner. Well, since hurricanes aren't perfectly predictable, nobody can get up here in this upper left-hand corner, and you're stuck trying to balance these two conflicting principles, if you will. So often to get a perfect probability of detection, you have to take on a high false alarm rate and vice versa. So what you've seen here in the colored charts is the Psurge as validated over 11 storms, 11 historical storms. The version that's currently in operations right now, as far as the new version that is about to go in production later in this hurricane season. So we won't talk about that just yet. I still want to focus kind of on this, the overall notion of this, or overall lesson of this particular plot. So this ends up being a really powerful way of talking about why we do probabilistic forecast, and then how we use those probabilistic forecasts to derive our forecasting system. So these little numbers here, this is a 0% exceedance, 10% exceedance, 20%, 30%, 40%, so on and so forth. So these are the so-called exceedances that we derive from the Psurge. So if you start up here, the 0% exceedance would be a worst case scenario. And so this would be analogous to what you've learned as a slosh mom in some of your other training. So it has a perfect probability of detection, but an extremely high false alarm ratio. So basically, this is, a broke clock is right twice a day. So if you always go to the worst case scenario for every storm, sooner or later, one will be a worst case scenario, but you inherited so much false alarm rate to get there. So it's not skillful in the overall scheme of things. But if you drop down to this 10% exceedance here, so if you go this way, notice how this line is substantially bigger than this line. Stated another way, you drop a huge amount of false alarm, and you only sacrifice a little bit of probability detection. So you can see here that you really bring down your false alarm rate without compromising your probability of detection. And you kind of see that through the 20% exceedance too. And starting about the 20% exceedance, you really start to fall off, and that slope kind of dies down. And at some point, you get to where you're just sacrificing so much probability of detection that it's no longer worth this little exercise. And so in this relative operating characteristic space, the 10% exceedance is best balances the probability of detection and false alarm ratio. Now, some people might argue, well, hey, why don't you go down here to 20 or 30 or 40% exceedance? Because remember that from a societal perspective, we're evacuating off storm surge. And so are we willing as a country to accept evacuations that are only 50%? Right. What if 50% of the storms, the evacuations were too short and we had to go out and rescue people? So that you always have to remember the consequence of the forecast and looking at it. The other misconception that we'll talk about here is a lot of people have said this 10% exceedance is a worst case scenario, or it's just slinging water everywhere. But when you look at it in this space here, clearly the 10% exceedance is not a worst case scenario. That would be a 0% exceedance, or a so-called slosh mom. So there's so much you can back out of this really powerful chart. This is how we grade ourselves internally. This is how we do verification when we're considering an upgrade. And we'll talk more about the upgrade in a second, but look how this upgrade, the blue version, is substantially better at all exceedances than the existing one. The blue line is closer to that perfection upper left-hand corner. So we were very pleased with this particular upgrade and looking forward to seeing it. The other thing that people struggle with is, why is Psurge only available through 48 hours? So I'm going to show you the same rock curve for 72, and notice how it collapses towards the no skill line. So I'm going back and forth between, that's 48, that's 72, 48, 72. And this isn't a function of slosh. This is a function of, at longer lead times, the errors in the hurricane forecast fan out or become so large that they themselves become dominant. And then just the ability to produce a reliable forecast is lost. And this is independent of the hydrodynamic or storm surge model one employs. So just because somebody can run a storm surge model, it's 72 hours or 96 hours does not make it skillful. In fact, I see a lot of academics running storm surge models 3, 4, 5 days before landfall. Those should be avoided at all costs because they are absolutely not skillful. Also, many of them are deterministic and not probabilistic. And deterministic approaches in storm surge are just not even remotely skillful. Now we're going to talk a bit, and this is, we're going to get out of the math here in a second, I promise. But we're going to get into why we must have so many tracks in Psurge. And the reason is you remember the cone is created by sweeping out a circle at each of the forecast times. So this highly realistic looking hurricane here, if we draw the circle around it constituting the error distribution, to get a track to sample this part of the circle right here, you kind of have to go a little bit beyond it. You can see why, that our tracks kind of have to fan out a little bit bigger than the cone, and I'll show that in a second here. And that's if you start to do the math on how many ensemble members you need to sample this entire space here. I won't take you through the math here, but it turns out it's actually for just a very typical storm, moving at a very typical 10 knots. It's on average about 620 tracks necessary. So 620 tracks, 620 individual slosh runs to produce a statistically reliable and accurate forecast. So if you're looking at any storm surge modeling that's only running one track, when theory suggests it should be 620, it should tell you something. Now Psurge, we looked at the average number of tracks over the last couple of years, and the existing version averages about 754, and the new version that's going to go in later this year about 659. So we drove this track closer to this theoretical desired goal here. Or stated more simply, we produced with this new Psurge a more accurate forecast while reducing the computational demand. Most modelers require more computational space or more computer power to generate a more accurate model. We actually produced a more accurate model while putting it on a diet, if you will. So there it is. That's the one that we'll talk more about that one in a second. That one goes in production later. And this RMW thing, I can't emphasize it enough because, there's storm after storm after storm that proves this is critical. And the most recent one, Crystal Ball, was the epitome of RMW, because there wasn't a lot of uncertainty in the actual intensity forecast itself, maybe 10 knots or so. And the track forecasts were just spot on from the Hurricane Center. So it really came down to the forecast was largely driven by what was going to be the RMW and the forward speed in this case. So if you look at the RMW from Recon from 2001 through 2018, and we limited this to within plus or minus 120 minutes of the Recon time to make sure, and the best track to make sure that we had a really solid sample here for evaluating this. So on the x-axis is intensity, and on the y-axis is the RMW, or size. Look at how much storms, the spread of storms here. So in general, as storms get stronger, they get smaller. So this is like the figure skater analogy. When a figure skater finishes up, they pull their arms in and it lets them spin faster. Similar concept here, but in these weaker areas here, look at the spread of potential RMWs here. You're basically spanning anything from about 10 nautical miles all the way to 150, 180 in some cases nautical miles. But what's more important here is RMW is in the denominator of the equation to count the number of tracks you need for Psurge. And so if you put a smaller RMW in this equation, you see quickly that you need a lot of tracks. Here, this is just showing you where we had the data to perform this particular analysis. So the bottom line is, if you didn't, if the math here, you don't want to suffer through that. RMW is important, really, really, really important. In fact, one of the most important things to predict storm surge, and it's often the most overlooked, unfortunately. Okay, if you got through the math, now we get to the good part, is how does all this work in a real storm, real example, real case? Well, let's go back to the most recent storm that we had when these slides were created, which was Dorian. So remember, Dorian parked itself off Southeast Florida as a Category 5 hurricane, and a pretty impressive event. So there are a lot of lessons that we can back out of it. Now I'm going to show you here the GFS model, or the so-called American model, is this blue. And wait a minute, you're saying, wait, there's multiple blue lines. Well, there's not one American model. There's 21 perturbations of it in its ensemble. And that's what we look at. We don't look at the single track or the single run the way a lot of people look at it, because that's not the most accurate way to look at that model. Also, here's the European model in green with all of its various ensembles. And finally, the UK Met model in pink with all of its various ensembles. The reason I show you this, because remember I told you earlier that these three models constitute typically the more reliable track models, especially if you're looking at the ensembles like we are here. Collectively, you can see the spread of possible tracks, or the forecast uncertainty that we were forced with or looking at in Dorian when it was situated off the coast of Florida here, approaching the coast of Florida here. And so everything from a, almost a due west strike into South Florida here, major hurricane striking South Florida, to a recurvature off the coast far enough that the impacts to Florida would be minimal. I mean, if we would have gone along the far right-hand side of this, you've probably gotten some swell and some beach erosion, maybe some outer rain bands or something, but not a big event. So everything from a full-on Cat 5 plowing into the coast unabated to sweeping out to sea a little bit. And this is what emergency managers have to make a decision off of in terms of evacuation. So if they assume something way over here and it plows into the coast, then that's really bad for life safety. And similarly, if they order a mass evacuation of major metropolitan areas and it sweeps out to sea, then that really hurts credibility. So how do you make sense of all this? How do you synthesize all of this and make a forecast and make an evacuation decision that is, sort of balances these two competing demands, if you will? Now I've sort of overlaid the cone. So this is the NHC forecast cone, we just chose orange here to make it pop off the map a little bit. And so something's starting to jump out at you here. You see these UK Met tracks down here in South Florida are outside of the cone. So something's going on here. Something's, you can start to see a little pattern here pop out. And since Psurge is based off the official forecast and roughly mimics the cone, you can see that in these gray lines, the Psurge tracks that drive storm surge didn't dip down here in South Florida. So why is this even remotely important? And there's the Psurge tracks versus the cone. Really quickly, I just want to prove to you that this is a real exercise. The European model, which is this EGRI, was the best performing global model during Dorian, and is typically among the best performing models each season. So these are the last three seasons: 2019, 2018, 2017. Quickly though, the Hurricane Center. Oh, and I'm sorry. This is skill. This is skill. So better skill or better performance is up on this plot. So you want to be up top on this plot, not down low. So the higher up you go, the more skillful you are. The Hurricane Center official forecast is black. You can see it just beats all these global models, consistently beats all the global models in forecast skill. But the reason I showed you this is to show you that during Dorian, the European model was the best performing model for that particular storm. So one could not just dispute these tracks out of hand. It's easy to say now, hindsight's 2020, that they were wrong, but you couldn't dispute them at the time. So how do you reconcile this? How do you brief an emergency manager here in Miami-Dade and Broward County based off this information? So what you're seeing here is storm surge. This is a meow, so-called westward moving meow. So this is the storm surge that Miami-Dade would have gotten if Dorian would have plowed right straight west into Miami-Dade at the sort of a worst case scenario, if you will. And if you're not familiar with South Florida, Miami-Dade is here, Miami is here, Fort Lauderdale is up here, and Palm Beach is up here. So this is Miami Beach. You can see complete and total overwash and inundation of Miami Beach, Key Biscayne. This is Coral Gables, Kendall, some of our bigger suburbs of Miami. This is disastrous. I mean, this is beyond what any of us can comprehend. The water gets up through the canals systems, if you will, in Miami River like this. Airport's up in here. So anyway, this is what an emergency manager would typically call an evacuation off of, and typically a Dorian storm would result in, if I remember correctly, about 1.1 million people evacuated from Miami-Dade County alone. That's typically how it would work. Now, what you see on the right is the Dorian real-time storm surge forecast that we produced, and this was publicly available. Anyone could have it. We gave it to emergency management officials in all these 3 counties. And if you're squinting and looking at the screen because you can't see anything, it's not an illusion. We literally didn't forecast any storm surge down in here. There's a little bit here in Palm Beach County. This was about 2 to 4 feet, and it was really confined right along the immediate coastline. So you compare these 2 plots here, and the thing that jumps out the screen here is I've heard people say our forecasts are worst case scenarios, or Psurge is just plowing every imaginable storm into the coastline and slinging water everywhere. That's clearly not true. And you can see that from this example, that we were predicting no storm surge or little storm surge in South Florida. And then if you drill in a little bit closer here, this is the same meow for up in Fort Lauderdale and Boca Raton area. You can see there was just nothing in our prediction. So what happened with the actual evacuations during Dorian? We went back and talked to the county EMs and the states regarding who evacuated and who didn't. And if you look at historical evacuation protocols, meaning how many people historically evacuate in a scenario like this, Florida should have executed about 4.5 million evacuations. In actuality, they only did about 1.4 million. That's a delta of 3.1 million. So 3 million people, or 3 million evacuations stopped by using this probabilistic framework. Similar numbers in South Carolina. Virginia wins the prize. Their Zone A evacuation zone, which is right along the coast, is 225,000. Bulk of that's in a Tidewater area. They only did spot evacuations of about 3,000 people, so that saved 222,000. North Carolina had similar results here, but they didn't have evacuation zones at the time of this, and I wanted to have a clear, make this fair and equitable in the analysis. North Carolina is launching evacuation zones for the first time this hurricane season. There's actually several opportunities to learn about that this upcoming week. If you want more information, email us and we'll set you up with that. So North Carolina has similar results, but to keep this fair, this analysis fair, I left them out. So if you added it all up, we should have, in a Dorian type situation based off historical protocols, evacuated about 6 million people and instead we evacuated a little over 2 million. That is substantial. I can't emphasize enough how big of a deal this is from an evolution of the hurricane program and evacuation protocols by emergency managers. I mean, this is a substantial accomplishment if we can continue it over the course of many storms. One storm does not a story make, so we have to see if this continues, but this is remarkable if it holds for the next several storms, because what happens is if you order someone to evacuate and nothing happens, then they won't evacuate the next time. So it's imperative from a societal perspective to cut these evacuations down to as little as possible without hurting anybody, which was go back to that relative operating characteristic chart. You want to move the false alarm ratio down as much as possible without sacrificing probability of detection. And that's what we think we've accomplished with this 10% exceedance in the probabilistic framework. We're able to cut or pull back unnecessary evacuations without compromising anyone's safety. Now, the bulk of that Florida result came from Miami-Dade County and Broward County. There were zero, count them, zero evacuations in either Miami-Dade County and Broward County. Now, if this sounds like no big deal, I've lived down here 20 years, and I'm still shocked that these two counties had the intestinal fortitude to pull this off. And I just spoke with the mayor of Miami-Dade yesterday, and he confirmed that this zero was because of the storm surge. Palm Beach County, I mean, this is really tough here to staring down the barrel of a Cat 5, only call 129,000. And some of this is mobile homes that you know, for wind. So some of this is and this number is even more impressive than it looks, but that is remarkable. And Palm Beach County is pretty densely populated. So the way they do this, the way what this chart shows is the evacuation zones on top of the whatever guidance that we give them at the time. So the summary here before we talk about the future is the use of probabilistic forecasting, at least in Dorian, shows early progress in cutting evacuation zones. So where do we go from here? Maybe I've kind of convinced you that this probabilistic framework is a good framework, but what do we do now? Where do we go from here? Well, what's new for 2020? The new version of Psurge, which I'm going to talk about here in a second, is scheduled. We're just waiting for a slot to get it on the new supercomputer, but it's running in parallel. It actually ran during Crystal Ball. We were able to look at it and view it. So it's running in parallel. We're just waiting to get it on the operational supercomputer some point during the hurricane season. I don't know that we're going to quite make July, but at some point in the hurricane season, we're going to upgrade to this newer version. And probably what a lot of you are interested in is this new experimental storm surge graphic that you saw launched during Crystal Ball. So I don't have a Crystal Ball's example in here, but I do have a Dorian example to show you what it is. It's basically a really simplistic, and you know what? A lot of the comments we got back during Crystal Ball were that people really liked the simplicity of it. It was just really super easy to look at and glance at and kind of understand from a geographical, regional perspective. These are the same numbers that have always been in the public advisory. So there's nothing new here per se in terms of forecast information. It's rather we're making it visually available in a graphic. So if you're used to seeing forecast numbers from the Hurricane Center in text only, it's the same thing except now placed on this graphic. The one thing to remember here, and people still struggle with this is aerial threat somewhere within the specified area, not everywhere within the specified area. So similar to the same sort of philosophy as a hurricane watch or warning area, somewhere within the specified area, not everywhere. So it doesn't mean that everybody in here is going to get 3 to 5. That means that somebody in here is expected to get 3 to 5 feet. It includes tide. I saw this a lot during the media coverage of Crystal Ball, is people, you assume these numbers are above normal tide levels. And no, our modeling system has a tide model in it, and so it's already inclusive of tide. So don't add anything to it or whatever. It's basically a total water level forecast. For areas that have steep bathymetry, Puerto Rico, Virgin Islands, places like that, it includes wave setup. We now have a new version of SLOSH which has a coupled wave model to it that computes wave setup. So don't add waves to it or don't double it because of waves or none of that stuff. So, you know, for these areas that have big wave impacts, it already has it in there. And, you know, we intended this to be primarily for media and social media applications. And looking at what I saw just in the few days of Cristobal, this is exactly what it was used for. It was heavily used in social media, and I've already gotten several emails from media partners of how valuable and useful this graphic was for them. So it's experimental, which means we're collecting feedback on it, which means if you have something you want to say about it, we have a formal process, a survey you can take to fill it out, or you can just email us. And it may ultimately evolve as we go through time. That's the whole point of an experimental product, to sort of put it out there and get feedback, and then take that feedback in, make any necessary changes, and then make it operational. So if all goes well, it would be an operational product in 1 to 2 seasons, 1 to 2 years. So if you have anything, feedback, send it to us. I got email contacts at the end of this presentation to help you with that. We already talked about this quite a bit, so I'm kind of going to skip over it. But the point of bringing it up was to tell you and remind you this RMW is really, really important. So what's going into the new Psurge that we're looking to upgrade to this hurricane season? It's basically improved RMW. So RMW is radius of maximum winds, or size, if you will. How big is the hurricane? And what you're seeing here is RMW error, how awful we are in nautical miles, in bias of the old version and the new version. So you can see here the new version, which is these dashed lines. It has a substantially smaller error. This is error up here, so you want to be close to 0. And it has eliminated a historically low bias in the storm size. So historically, our RMWs were too small. You see that in the bias. And this improvement in RMW is held through about 36 or 48 hours. So you get an improvement in the initialized system through about 36 or 48 hours. So I want to clarify, this version that we're looking to upgrade in 2020 has improved initial RMWs, not improved forecast RMWs, improved initial. And you can see the improvement. This is the existing operational, this is the new one. You keep that improvement, it manifests itself in forecast improvement through about 48 hours. So the way that we do validation, and there's a lot of interesting things. You'll see people on social media now, or anywhere now, in conferences now, they'll take one storm in one observation and they'll declare success or failure. Well, you can't validate a probabilistic system that way. You can't validate a probability against a water level or a wind observation. You have to do a reliability, what's called a reliability analysis, which means you have to do it over the course of many storms. In our case, we took 13 storms from 2008 to 2018. That spans the period of the USGS pressure sensor error, which means we had good, reliable data. This is the geographic distribution, so that you can see we're not, we don't have a geographic bias. For example, if you verify one storm here in Texas, that doesn't mean that the model's any good in New York, or vice versa. So you really need a geographic range of landfalls here. The little dots here in this diagram represent all of the observations that we used for this big study, and you can see the geographical distribution. So 13 storms, and then we verified the 12, 24, 36, 48, and 72-hour forecast points closest to landfall. 7 Psurge storms or advisories for each storm. So 13 times 7 times 2, the old run versus the new run equals 182 runs. So it took 182 Psurge runs to pull this off. And so we're going to go through some of the validation here. Really quick, we don't talk about NAVD88 externally in our public-facing forecast or briefings to EM. But to validate models or internally within the scientific community, we use NAVD88. So you're going to see me use NAVD88 probably one of the few times you'll ever see me talk about NAVD88 externally, because that's the best way to do model validation. So what you have here is the observed frequency versus the forecast probability. Stated another way, if you forecast it's going to rain, there's a 10% chance of rain, 1 out of 10 times the forecast should be right. Or if you forecast a 50% chance of rain, 5 out of 10 times that forecast should be right. And so what you're doing here is comparing the forecast probabilities against how frequently did it occur. So where you want to be is along this dashed line here. That's perfect. That's where you want to be in life. And if you're up here, you're under forecasting, and if you're down here, you're over forecasting. So again, you want perfect reliability along this dash line. Throughout these plots, the current version is going to be in red, and the new version is going to be in blue. Then down here, I'm going to show you the counts in each of the bins. So if we look first at the probability of greater than 9 feet NAVD88, so this is looking at how well does Psurge predict extreme events, big events, and this is looking at 36 hours, which is when we typically issue our warnings. You can see that the blue is the new line, and the first time our crew showed this to me, I asked them to redo it, because usually you don't get a reliability diagram that look that close. And you can see the old red line kind of fell off here a little bit. We kind of go through and look at it. So we're going to keep looking at these types of plots over and over again. And this is for 24 hours, a similar trend, 24 hours. We were under forecast, or sorry, over forecasting a little bit. The old one was over forecasting, and you see the new version that's going to go in production later this year has better reliability. Or I prefer these bulk statistics like this we showed you before. We're going to talk about individual storms here in a second, but these bulk statistics show you, I think, better perspective, and the new version is much closer to this upper left-hand corner. All right, most people don't like statistics as much as me, so let's look at things from a more realistic perspective. Let's go back and look at Sandy. And you can, if you remember, Sandy was a very large storm as it turned up the coastline, and you can see the old RMW versus the new RMW at each of the forecast times relative to landfall. And you can see that the new version is correcting the small RMW bias that we previously had. Let's look at Harvey, and Harvey is, so this is 60 hours before landfall. This is the current version of Psurge, 10% exceedance, and this is the new version. You can see a substantial delta here between the new and the old version at 60 hours, because it is correcting for this size issue. And you can see it here, the observed maximum was this little dot, this little star here, right here. You can see that the new version is better at correcting. It was higher in the beginning and lower at the end. So it corrects the low bias at the long lead times and the high bias at the short lead times. At least this particular example did. Similarly, if we go to 36 hours, which again is our warning period, you see a similar trend. It corrects this low bias at the early stages and high bias at the latter stages. So if you look at them side by side, if you just eyeball them, if you don't like statistics, you just eyeball them, you can see that the new version shrinks the storm surge area a little bit, or zeroes in on the area that was ultimately hardest hit from Harvey. So these results are really, really encouraging. That's why we went ahead and approved it for upgrade. Just again, waiting for a slot to get on the supercomputer, but it is running in parallel. We can see it internally, and we can use it for our forecast process internally. Since I'm guessing there's a lot of questions here, since we just came out of a landfall event, a rather significant one from storm surge, we kind of rushed through it a little bit just to leave the floor open for question and comment, and sort of let this go to where the audience will go. And Cody Fritz has joined us as well. Here is some contact information if you need to reach any of us, or if you have comments about that new forecast product that I showed you, or if you have comments in general. I mean, feel free to reach out at any point in time. And I guess Robbie will open it up for questions if you're ready.
Yeah, thanks, Jamie. So we still have actually 45 minutes, and we only used half the time. So we have plenty of time for questions. I should note that Dan Brown is now on, so he's going to help moderate questions as well. Before I turn a question to you, I did want to mention that when you were talking about the storm surge product, somebody asked about providing feedback. You've provided emails here to get in contact with you. I actually also shared a web link there in the question box, which is for the experimental product, and there's a survey link in that link where you can fill in your opinions and thoughts on the product as well. So what we'll do is after the season, we'll kind of go through and look at all those comments, and it will help us decide what to do with the product going forward. First question is from somebody who's asking about that product. I think I kind of already answered his question, but it's probably good for everybody to hear it. He said, will this new storm surge product be available for GIS use, particularly ArcGIS?
Yeah, so excellent question. We get a lot of that during its launch. During the experimental phase, we primarily put a graphic, just a flat graphic out there, and solicit feedback. The reason being is if we put the underlying data out there, people start writing, rightfully so, code and scripts to use and manipulate that data, such that if we change it, it really screws up everybody's codes and scripts, and we get a lot of unhappy customers. The point of an experimental product is to be responsive to our constituents' input. And if we put the data out there, we can't be responsive. We're sort of locked, if you will. So during the experimental phase, it is not available, but we have absolute aspirations to make that available once we've worked through all of the feedback, made any changes that we need to make, and lock it down as permanent. So what this prevents is us constantly changing it during storms or mid-season, and everybody constantly having to rewrite their codes and scripts. So yeah, the answer is yes, but just not this hurricane season.
Okay, so another question here is actually a good question, because I was going to ask you to elaborate on Cristobal a little bit. And I think this question kind of hits that one directly. So this is an operational question. During Cristobal, I did not see any Psurge data on the FTP site. So I guess, Jamie, if you can answer why that is, and specifically what it is you guys had to use because of Cristobal's structure, or why it was so unique.
Yeah, so we actually have a probabilistic, a similar probabilistic forecast system for extratropical systems or non-tropical systems or winter systems, and it's called PETS. And after working with the hurricane specialists, we decided that the structure was better reflected in this extratropical version of the probabilistic system, and we used PETS. And so we didn't run Psurge in this particular case because it just, quite frankly, wasn't reflective of the storm. And it produced storms that were too small, because if you remember, the actual storm was, the RMWs were over 100, 150 or something like that. And its large wind field, parametric wind models, which is what drives Psurge, can't really reflect well these asymmetries like you saw in that particular case. So we went with the probabilistic extratropical storm surge guidance, or PETS, in that case. We have the ability to dynamically switch between them, either from storm to storm, or we can actually switch in during the middle of a storm. And so we were monitoring Psurge to make sure that it was, if it ever became more reflective of the actual event, we could have switched to it. But the storm never consolidated and got a small enough RMW that was necessary.
Hey, Jamie, this is Dan. I was able to join a little late, and with Robbie here, we're looking at the questions. Folks, be sure to ask those questions because we are here for this discussion and have plenty of time here. One thing I was going to ask you to see if you could elaborate on, because I know that we do have attendees from the Caribbean that go to the National Hurricane Conference. So I was going to ask you if you could describe a little bit about the international plans I know that you guys have been working on, about some of the expansion that's going on into the Caribbean.
Yeah, it's something near and dear to my heart. Under the partnership we have with WMO and the member nations within the Caribbean, we have commenced an effort to expand our storm surge modeling capabilities into the Caribbean. The one thing to remember here is that the countries retain the ability to forecast and warn. We're just supporting them with science and technology and training. So we've already launched and finished an initiative in Dominican Republic and Haiti. We have Belize and the Yucatan Peninsula of Mexico underway now. That should be finished by the end of the calendar year. And we've just agreed to start the Bahamas in 2021. It'd probably take about two years or so to do the Bahamas. So maybe by 2023 or so, we would have the Bahamas done. That doesn't mean that the rest of the Caribbean is left out. It just means that you can only do them, so many at the time. And the prioritization was by our sponsor, USAID, was such that that's the order that they asked us to do them in. But in all likelihood, we're going to do much of the Caribbean and cover much of the Caribbean. But just to remember that the countries themselves retain the ability to make a forecast and warn. We're just supporting them with these modeling initiatives.
Hey, Jamie, next question. One of our good friends, Lenny, actually, it says, what should the public understand about potential worst case scenario with 10% exceedance? Because sometimes I'm not sure it gets explained in the best way possible. So when we say reasonable worst case scenario, what should the public do with that sort of information?
Yeah, I think the public, when they hear worst case scenario, they think of it differently than scientists and EMs think of it. And so the public hears worst case scenario, well, I'm not going to pay attention to it. It's not going to happen. Or it's some far-flung scenario that's not realistic. The 10% exceedance, as we've shown in this series of slides, is far from a worst-case scenario. It's what you should plan for. It's sort of like Robbie uses this analogy of traffic. That when you go to drive to work, the traffic might cause you to have a commute time that ranges between 30 minutes and 1 hour. Well, if you absolutely cannot be late to work, let's say you got something going on where if you're late to work, you're going to be fired. You're more than likely going to skew towards that 1 hour commute estimate versus that 30-minute commute estimate because you have no tolerance to be wrong or to be late. Similarly, though, if you can just show up to work anytime you want, then you might skew towards that 30-minute commute time estimate. When it comes to storm surge, and given how deadly and consequential it is, you have to skew towards that 1 hour time frame because you have no ability to react or contend with a scenario if it comes in closer. You don't want to lose your job if you show up late. So the 10% exceedance is what people should prepare for and execute on. Don't worry about what it is. I hear people falling down over the 10% exceedance and trying to explain it. And I see people trying to breathe 10% exceedance and just getting themselves all twisted in knots. All you have to say is, given the uncertainty here, this is what you should prepare for. And that's it. If people would just brief it that way, we would go a long ways in this country at cutting the impacts from storm surge. So great question.
Lost the window to unmute myself for a second there. Sorry about that, Jamie and Robbie. I was going to, Jamie, just ask you another question. I see another question was popping in as I was coming off mute here, so maybe Robbie can take that one. But I was going to ask you about maybe describe a little bit about the WFO collaboration process between for the storm surge warning. I just thought folks might really like to know how that we use the expertise at the Hurricane Center and the storm surge unit, but also the local office expertise to come up with that watch warning area. We've been doing it now for, I guess this is what, the 4th hurricane season now. We started in 2017. And just to say, how is that process going? And, you know, are we really leveraging the expertise of both centers?
Yeah, and I can tell you an example from Cristobal that really hammers that home. What we're trying to accomplish from a warning perspective in Cristobal is to warn for that, you know, pretty impactful storm surge that you've all seen in media coverage and social media. I mean, clearly that was a big deal and more than justified the warning. But for those that don't know, Louisiana is very much a leveed area, meaning much of the populated areas are protected by levees. So what we were trying to do is prevent people that were safe inside a levee from getting a warning message that said life-threatening conditions. You can imagine, you know, storm surge was somewhere around 5 or 6 feet, and you can imagine a community that's behind a 15-foot wall getting a warning message that said leave, you know, evacuate. Obviously, that would be really destructive for credibility. So what we did with this collaborative forecast process and the WFOs impacted is we were able to go in and just meticulously draw very, very, very carefully. I think it took hours to do this, so that we were warning those outside of the levee areas without over-warning people inside of the levee areas. And we have this process where we can share data back and forth with the impacted WFOs via AWEB. So we can draw something up and send it to them, and they can come back and say, you know, it's a little bit too close to the levee. Can you trim a little bit out? Or they can trim it out themselves and send it back for us to evaluate. And so this iterative process can go back and forth as many times as necessary to really refine the process. And this was a case, Cristobal was a case of we had to go back and forth several times, especially with the weather forecast office in Slidell, to basically to surgically draw that warning to prevent overwarning from occurring. So yeah, great question, Ben.
Another Cristobal question kind of goes back to the reasonable worst case scenario discussion we just had. I think you already hinted at this in the previous answer, but with 3 to 5 feet of storm surge that was forecast for portions of the Gulf Coast, this person was curious to see how did that compare to the reasonable worst case scenario ideology. In other words, if the guidance that you had, how did what actually happened, how did that compare?
Yeah, so I mean, we had guidance that suggested we were going to be substantially higher than we observed. And the 3 to 5 feet, we don't yet have all of the observations. Like I was still getting input from Army Corps this morning. But of the available observations that we have, assuming they're not contaminated by heavy rain, and we won't know that for a while now, the peak inundation was somewhere in the 5 to 6 foot range. So the 3 to 5 is you know, if I'm off by half a foot, I'll take that every day of the week. I mean, it's because it's just so hard to forecast these things. And so, but more importantly, you know, everybody gets hung up in the numbers. And that's not the most important thing. The most important thing is the warning area. In the warning area that I just talked about, that we did in collaboration with the Weather Service Forecast Office in Slidell, that warning area is probably the most accurate warning we've seen since the implementation of this new storm surge warning paradigm. The warning message is what's important to me. We spend more time defining that warning area than anything else, certainly more time than doing the numbers. The numbers form a reference point for people to kind of get a sense of what area is going to be hit hardest, but I'm more impressed with the warning area and how well that verified. There's no such thing as a perfect verification, but that was pretty dang close. So I hope I answered your question.
Jane, I was going to also ask a follow-up to that, because if everybody was paying attention to the forecast and watches and warnings during Cristobal, they may have noticed that there was actually a broken storm surge watch. In other words, there was a piece of the coast that was not actually under a watch, but yet it was bookended by watches even all the way east to the Big Bend of Florida. So I was wondering if you could talk about, one, the rationale behind that, and then two, kind of the watch warning philosophy, and that you can still have watches up even if you don't necessarily expect the surge, but there's still a possibility of the surge.
Yeah, so early in the forecast process, so when the watches first went up, the projected wind field was a little bit bigger than what ultimately happened. And what that was doing was putting strong southerly or southwesterly flow into the Florida Big Bend in the west coast of Florida, west coast of Florida, north of Tampa, if you will, over to like St. Mark's area. That portion of the coastline is one of the most susceptible portions of the coastline. I mean, really 25 knots out of the wrong direction will cause pretty substantial storm surge, even 20 knots sometimes. And so that big wind field was producing, 20 to 25 knots over there. So we put up a watch initially to cover the potential. Ultimately, the wind field shrank and we didn't have to upgrade it. In fact, we replaced it. The Weather Service office replaced it with a coastal flood warning. And they actually did get pretty substantial storm surge, just not to the criteria of a storm surge warning. Then west of that area, there was a stretch along the Florida Panhandle into coastal areas of Alabama, where it takes, there are certain portions of the Florida Panhandle where it takes, 50, 60 knots of wind to produce a substantial storm surge event. And in this case, it was going to be shore parallel, blowing parallel to the coast versus perpendicular to the coast at about 30 knots. So we were able to break the watch area up into two distinct pieces, which when it first came out, people were, completely confused because everybody's used to a continuous watch warning area. But that sort of speaks to the versatility of our new warning program, is we can put the watch or the warning up wherever it needs to be. Geographically, we can just do what we need to do based off the threat. And that was a classic case of sometimes the threat is not always continuous. And then as we marched again to the period of a warning, which is 36 hours, the easternmost area over in the Florida Panhandle, we didn't have a need to upgrade it to a warning, so it got replaced with the coastal flood warning.
So Jamie, I'll ask you one here as we see if we get any more questions before we wrap up. But I know you've been in the job for a while, and before that you were a hurricane specialist at the Hurricane Center. You've seen a lot of impactful storms in the last, 15 or 20 years. Of course, there's been Sandy, Ike, Michael, Dorian last year. Some of those real significant storm surge events. Just throw out there, what event sort of keeps you up at night? I know we have a chance to talk to a lot of emergency managers. We train those folks. You get to talk to a lot of them. So what particular event would really concern you, or one of the past, had it been slightly different, could it come out differently or potentially worse?
Yeah, my response is going to be contrary to what people think. Most of the areas which have been recently hit by storm surge have some sort of awareness of their vulnerability. And when we engage them, or the local emergency managers or elected officials, we just have very little resistance to talking about flood potential. It is the areas that have not been hit in a long time where there is a dearth of knowledge and experience. And the Florida West Coast is an absolute disaster waiting to happen. because it is one of the most vulnerable areas for storm surge. So I'm talking like, Fort Myers, Marco, all the way up through, Tampa and points north. It doesn't take a lot of wind to produce a back crushing storm surge in these. I mean, I'm talking Cat 1 winds will be absolutely devastating. And yet I don't think the population understands it over there. Many of the people who live there now have relocated from points north. Even if they've lived there for 10 to 20 years, they probably haven't experienced the full wrath of a hurricane, much less a major hurricane. And so there's just so little historical knowledge of storm surge in these areas. And I fear it's going to result in complacency, lack of evacuation, and heaven forbid a storm ever goes over there, we're probably going to be looking at a pretty big mortality or drowning from storm surge should that ever occur.
Yeah, I'll follow that up real quick, Jamie. I'm glad you mentioned the Florida West Coast. Last year or a couple years ago with Irma, his name escaped me for a second, with Irma, the Keys certainly had a great impact. You had a chance to go down after that storm. But then again, the West Coast, I mean, you showed some slides last year, just how sensitive the track was to the vulnerability of the storm surge along the Florida West Coast with that particular storm. And I would agree that I don't think folks have experienced over there. Maybe you can comment a little bit about Irma and had it just shifted, what a difference it would have made in that track and in that surge. And again, the last big storm, a strong storm to hit there, I shouldn't say big, the last strong storm to hit over there was Charlie in 2004. And that was a very small storm, and how his surge was much less than it could have been because of the size.
Yeah, I mean, there's so many good things to unpack there. To start with Irma, because that's where you started. We've actually run the scenario where if Irma would have made landfall a little bit further west, exactly 30 miles, if I remember, Naples would have been absolutely crushed. And instead, they were on the backside or where the winds were blowing offshore. And the worst surge basically went into largely unpopulated Everglades. So, hit areas like Everglades City and places like that. But again, the populated locations were spared by this little jog to the right. And the other thing is the wind field kind of fell apart on the west side. If the storm basically became half a storm. And so I heard, and I still hear residents in Naples, dismissing the storm, blowing it off, saying the forecast was bad. We've even got people that were mad at us for that forecast. And man, if you would have been in the Keys and saw the damage that they experienced, if I were a Southwest Florida resident coming out of Irma, I would be thanking my lucky stars that system made those last minute adjustments and spared them the worst of it. You really dodged a bullet over there on the Southwest coast. And then Charlie, a lot of people think because they went through Charlie, they've experienced the full wrath of a Cat 4, but Charlie was a tiny, tiny system. So a lot of people really didn't experience Cat 4 winds. And those that didn't experience Cat 4 storm surge because the RMW is only like 6 or 7 miles, I think. You take that exact same storm, exact same track, and give it a 20 mile or 25 mile RMW, and we'd still be picking up the pieces over there. Literally, we'd still be recovering from the storm surge had that happened. You can't use those historical storms as a proxy for risk. And I fear, at least on the west coast of Florida, what I've seen thus far is people are using what little hurricane experience they have over there to ascertain their vulnerability to hurricanes. And that's just going to be a devastating impact if we ever have a large RMW storm hit populated areas of the Florida West Coast.
Jamie, I was getting ready to ask you a question of my own, but you've been saved here by somebody else in the question box. They're saying, what are your thoughts on Northeast Florida? They have historic flooding along the St. Johns River in downtown Jacksonville from Irma, from a storm that didn't even make landfall on the East Coast, which does make it easier to communicate.
That's a great question. So if you remember Irma, as it turned the corner and kind of expanded out and moved over Florida and, on up the East Coast, it produced this really prolonged northeast wind that wasn't that strong. I mean, it was, if you remember correctly, it was probably 30 to 40 knots of east-northeast wind that just blew right into the mouth of the St. Johns River. And so it just clogged it up and choked it up as that heavy rainfall came down. So the rain, which would have normally wanted to, flow out of there with gravity, you got salt water coming in one side and rain coming in the other side, and it just produced pretty substantial storm surge, or combined rain and storm surge flooding, that people said they were caught off guard because they were looking at the storm from a traditional perspective. It's Saffir-Simpson scale and their proximity to the center. And that's a classic example of how viewing a storm through those lenses will burn you, because if you would have looked at the forecast storm surge, it was well forecast. And so that's why people have got to stop looking at storms based off the Saffir-Simpson scale and their proximity to the center. And that's why we ask our media partners to do the same. We ask our media partners, when they're talking about these events on air, to not stress so much the track, or proximity to the track. I mean, I literally see people on air saying the track has moved 5 miles since the last advisory, and that's so ridiculous to focus in on that. We should be focusing on the hazards and the impacts, because that's what will help people make really good decisions.
Dan, I had another question of my own I was going to ask.
Oh, this is going to be a hard one.
So, it's probably hard to believe, but it's now been 15 years since Katrina. It's just mind-boggling to me. But now you think back, Jamie, to since Katrina, and now since all these new storm surge products have come online, it's a little bit of speculation, but you and your team were going to be providing some science related to Katrina in a scientific meteorological conference this year. Because of COVID, that didn't happen. But at least from what you've seen, how do you think all the new products would have possibly changed some of the outcomes in Katrina?
It's a good question. So it's hard to know what would happen from a societal perspective, how people would interpret and react to the forecast. But I can say with great confidence that given the technology that we have now in front of us, because we've gone back and rerun it, if a Katrina case were to ever form again, we would absolutely predict and clearly communicate overtopping. So we would clearly convey the potential for substantial amounts of water being inside the hurricane risk reduction system and flooding much of New Orleans. Now, how would that manifest itself in terms of evacuations or evacuation compliance is really hard to know. But I think it's hard for me to imagine that if the Hurricane Center loudly declared overtopping as possible and included that in all of its messaging with sufficient lead time, that at least some of the people would leave, or the evacuations would be somewhat earlier in the process. And it's hard to not imagine how that wouldn't cut mortality if we had to do it all over again. I don't have any firm numbers to say how many people would have changed their mind or would have done it differently. All I can tell you is the science we have now would absolutely enable us to predict overtopping and message it.
And I'm also wondering further east in Mississippi, and now you're able to show how far inland that surge could go. And I don't think maybe a lot of people in Mississippi understood before Katrina it would go that far inland. So I think that's what they're asking.
Right. So especially now that we've had these high resolution inundation maps that emergency managers can use to overlay on their evacuation zones and make evacuation decisions. But the other thing that's starting to come out of our science too is, I alluded to this earlier, we have a version of slosh with waves. So if you remember in Katrina, the violent wave action in Mississippi, the Mississippi coastline, just absolutely destructive. It wasn't just a surge and the depth of the surge, but the presence of violent waves that was really did that area in. We've got new tools now to help us sort of isolate where this violent wave energy is going to be. And in those cases, we can work more closely with emergency managers and strengthen our language, if you will. Whether it's harsher call to action statements or harsher external messaging. I can give you an example of that from Hurricane Michael. There was a news report of an individual that had stayed in a certain location, and I was almost certain that that location was you could not survive. And so we called the local authorities and said, is this true? Is this individual still there? Well, then go in and get them out. So you can see that sort of advanced science is enabling us to really dynamically adjust to these storms and give increasingly more refined guidance to emergency managers.
So I had one more question for you, and I think you just answered. I was wondering if you could talk about looking into the future about forecasting the environment of storm surge. You kind of just mentioned it with the violent waves, but there are some storm surge events that aren't quite so violent. So I know that you and your team have been kind of looking at that as well.
Yeah, so there's this thing called still water, which is or still water depth. So what we're doing now is we're primarily predicting how deep the water will be and how far it will go inland. We're not predicting the violent nature of that water, because in some cases it comes up gently and just floods a little bit, and in other cases it comes with waves and basically rips everything off its foundation. It's not survivable in those environments. So if you contrast the environment of Hurricane Michael in Mexico Beach versus Florence in New Bern, that's still water versus high velocity wave energy. We're getting closer and closer to being able to differentiate those two, or state it more simply, identify the very high velocity violent wave areas in a storm. Armed with that information, we think we can equip emergency managers with better tools to make increasingly more refined evacuation decisions. So for example, in a Michael case, as we progress better and better, deeper and deeper into the science, this new science era, if we had Michael to do over again, I think we would have, with the science I've got now, we would have called emergency managers and basically said, go door to door if you have to, and get everybody out. There's just no chance of surviving this environment, and that might change the way they evacuate, hopefully for the better.
Thanks, Jamie. I have not seen any more questions come in recently, so I think with that we'll start to wrap up and give folks back a few minutes of their day. Do appreciate everyone joining us this afternoon, and as always, thank the National Hurricane Conference for organizing these virtual workshop sessions. Again, it's disappointing that we all couldn't be together in person earlier this year, but very happy that we were able to provide at least a few sessions over the last week or so, and this one today, regarding some of the topics that we were going to discuss at the conference. So it was great having folks on with us, and I know that they have been recording these sessions and putting them on their website. So you can look for and share the recording with others if they weren't able to join today. So again, thanks, and thanks you, Robbie, and thanks, Jamie. Not sure if either of you have any final words, but I'll sign off for now.
I'll leave you with this last slide that has the contact information of people you can reach out to before, during, or after a storm with questions or concerns. We love hearing from our constituents. It typically guides how we do things in the future. So if you've got opinions on how we can make things better, or the things that we are already doing, let us know, and we'd be happy to hear from you.
Yeah, thanks for adding that, Jamie. And again, thanks everyone for joining. Hopefully it's a quiet hurricane season. We don't have to talk to many folks this year, but we will see. Be prepared. Thanks again, everyone.
Yeah.